video, we implemented a very simplistic algorithm based upon a very simplistic strategy based upon this moving averages, right? And we were using 3-day moving average and a 5-day moving average. So if the 3-day moving average crosses above the 5-day moving average, then we go long, right? And then if 3-day moving average goes below 5-day moving average, we go short, right? And it turned out to be a strategy that actually gives you positive returns, right? So using our data for TQQ, that's a leveraged ETF, the return was, if you are using stick with 3 and 5, the return was like 3 times, right? 3 times, it's going to triple the amount of money that you started with 5 years ago, right? So one of the questions I got from students was about why 3 and 5, right? Is that some kind of magical number, or is there better choices? Are there any better choices than 3 and 5? Right? So that's gonna lead to a quite important discussion about something that's kind of inherent to any kind of a machine learning algorithm, which is called overfitting. It's not just this kind of overfitting problem is not just unique to this kind of simplistic strategies, but also to any kind of machine learning technique, including those sophisticated ones based upon deep neural networks, reinforcement learning, or any kind of a machine learning algorithm has this kind of a very difficult to solve problem called overfitting. Over the years, people have come up with different strategies, right? Some of them are quite effective, and we're going to talk about those things later on, right? But in today's video, let's just use this very simplistic example based upon these moving averages to look at and try to understand what exactly is overfitting, what overfitting actually means, right? What overfitting actually means, right? The problem is quite small, right? It's just one ticker symbol, and then the parameter that we're going to try out is just the 2 numbers, right? Here we are choosing 3 and 5, right? But is that the best number? No, it's not. It's not. You can find better numbers. You can find better numbers than 3 and 5, right? And we're going to look at how we can find those better numbers, right? Today we're going to use a very brute force technique, right? Just by searching through all possible numbers and see which one actually gives us the best return, right? And later on, once we start to deal with neural networks, we can talk about very specific methods, right? Some of them are related to regularization techniques, right? If you have watched my videos about regression, you probably have some idea about regularization. Some of them are related to parameter space techniques like dropouts, right? We're going to talk about those things. But before we get into the details, let's go through the disclaimer. All examples and code presented in any of my YouTube videos are technical and illustrative in nature and do not represent any financial recommendation or investment advice. Right? So last time we were working on so we computed this kind of moving averages, right? For 2 durations, right? 2 window size, and then we computed the return by going through all those different lines of code, right? But let's because we are going to try out different numbers now. So it might be convenient to define more functions, to define some functions to encapsulate all those calculations, right? The first thing we're going to do is to define another function here. Let's just call it get SMA return, and this function is going to take a data frame. Let's call it df0. That's the input data frame, and then a short-term moving average window size S, a long-term moving average window size L, and then if we want to make plots about the evolution of our cumulative sum of the returns, let's give it like p flag. Right, so if the p flag is true, then we can make a plot. This function is going to make a plot. If p flag is false, then we don't make a plot. Right. The first thing I want to do is to actually duplicate the input data frame. The reason that I want to make this duplication is because I'm gonna modify this input data frame, and if I want to reuse the input data frame later on, I don't want to use those modified data frames. So I just make a copy, make a duplication. That's a hard copy. That's a deep copy. It's not a shallow copy. If you know something about deep and shallow copy, this particular function called .copy is gonna make a deep copy. So it's a separate memory space. It's not gonna touch the memory space that's occupied by df0, right? And now I can make whatever changes I want on this duplicates, right? On this duplicates. So the first thing I'm gonna do is to maybe I should just copy these codes over, right? So instead of calling it data, df, right, SMA, let me just call it short, right? That's gonna be df, the closing price dot rollings, s, right? That's the s, short time duration for the window size, right? And I can do the same thing for the long, right? And then L, right? And then I can just drop an A, right? Oh, sorry. Right. So that's this part of the calculation is done, right? And then let's move this part of the code to inside of that function also, right? The first thing we are going to do is to actually copy over this this line of code, which is the code for us to actually compute our positions. Is it a long position or is it a short position, right? df position equals to np where df SMA S and n SMA long, right? So if the short-term moving average is larger than long-term moving average, I go long, so the position is going to be positive one, right? And if it's the opposite, then I go short. But I go short not by sort of, for TQQ you can go short by selling out all TQQ and buying the so-called SQQQ, right? SQQQ is also 3 times leveraged. It's like the opposite of the TQQ. So if TQQ or QQQ actually goes down, SQQQ actually goes up, right? So if one of those symbols is called SQQ, right? So if you are a retail investor, you probably knows about this particular strategy, right? So if you want to make a profit when the market actually goes down, when QQQ actually goes down, SQQQ is going to go up. So you could actually make money by buying SQQQ when the market is down. Right? But this time we are not going to do that. We're just gonna choose 0. 0 just means that I'm going to sell all my positions on TQQ, my long positions on TQQ. Right? So I'm just going to close all my long positions. That's it. I'm not going to open any short positions at all. Right? And later on, if you experiment more about this parameter, change it to -1 or something, you're going to find out changing it to -1 doesn't really increase your profit. It actually decreases your profit, right? Especially for this kind of a moving average based strategy. You can try it out once you have the script. You can practice by yourself. It's not hard, right? But that's how I actually compute my positions, right? But in order to compute this position, I'm gonna need my NumPy library. So I need to move this line of code also to the top, right? So I'm gonna import. Maybe I should import NumPy first and then pandas, right? Because that might be better, right? And then don't forget about this kind of shift to remove the four-side bias, right? Because our calculation is based upon the closing price. So whatever position that we want to change, we have to do it on the next day. So that's why we have to shift it by 1, right? And then all we have to do is to actually multiply our positions with the with the daily return, right? With the daily return of the closing price. That's where is that? Okay. I'm gonna call it SMAR is gonna equal to position multiplied with DFCR. That's the daily return of the closing prices, right? And if P flag is true, so which means that we have to make a plot about the curve, right? The return curve, right? How it actually evolves with time, right? Then we do this come sum, cumulative sum, and then apply np.exp, right? And then just dot plot, right? And then we can make a plot about the cumulative sum of all the returns. And then the number that we want to return, is actually the last point of this cumulative sum, right? The last point of this cumulative sum is actually the sum of all the numbers in the DFSMR, right? And then we take the np.exp on that, right? So all we have to do is to do this DFSMR.sum, right? Sum up all the numbers inside of this column, right? And then because it's just one number, it's not a sequence of numbers or time series, so we can just do np.exp on it. We don't really have to call this dot apply method, right? And that's it. That's this get SMA return function, right? So if you call this function with a specific choice of S and L, right? That's these two moving averages, right? In the last script, we were using what? We were using 3 and 5, right? If we are using this 3 and 5, then we can get a specific value, right? Specific value. But let's try it out to see if this function is any good, or do we have any kind of errors in it, right? Let's just run it and see if we can. So here you are computing the CR column, right? And then all we have to do is to actually print get SMA return, and then we're going to give it our entire data frame, right? Because we have both the C and the CR columns, right? The short term is 3, right? The long term is 5. And then let's make a plot, right? See if we can recover the results that we got from last time. And let's just run this script and see if we have any errors. Okay, so is it running? Okay, that was the figure that we got last time, right? It's about 3.07. That's about 3 times, right? That's exactly the same numbers that we got last time, right? But now the question is that why 3 and 5, right? Can we find better choices? So if you want to find better choices, what might be a possible algorithm to find those best choices for the two moving averages, right? By the way, one of the reasons for using 3 and 5 is because one of those pioneers in technical analysis, whose name is Gan. I think did I spell it right? I'm not exactly so sure, but because maybe I should just do a search. Gan was one of those earlier pioneers of technical analysis. Let me see if I can find. Maybe this is not a good place for me to actually do that. But the reason that we are looking at these two numbers is because these two numbers are two numbers inside of this Fibonacci sequence. So if you know about Fibonacci sequence, it goes like this. The first number is going to be 1. The second number is also going to be 1. And then the third number is going to be the summation of the previous two numbers. So 1 plus 1, that's going to be 2, right? And then what's going to be the fourth number, right? It's going to be 1 plus 2, that's 3, right? And then what's going to be the next number? It's 2 plus 3, that's 5, right? And then the next number is 8, this is 13. It can go on like that, right? This particular sequence of numbers is called Fibonacci numbers. And what Gann found in the early days, he was very, very early, 1930, 1950, that kind of a time range, right? During his time, he found that this particular Fibonacci sequence, the numbers from those Fibonacci sequence, seems to work particularly well in the stock market, right? If any of those parameters, if you have to set up any kind of parameters, numbers from those Fibonacci sequence seems to be working much better than other numbers, and from that time, and then more and more people start to adopt those numbers in their own trading process or in their own trading practice. And then if you have more and more people start to using it, gradually it becomes even more effective. It had this kind of a self-reinforcing effect. So by this time, by the time that computer comes around, lots of people were actually using those Fibonacci numbers, right? But that was before computer was widely adopted, right? After the computer age, everyone starts to trading on their computers. Those numbers are not exactly that effective anymore, right? And that's one of the reasons why we are looking at more sophisticated machine learning techniques. Those are experiences that we gain from many years ago, decades ago, may not be applicable to today's data, right? So if you want to find a better choice of those numbers, how are you going to do that, right? How are you going to do that? One of the most straightforward ways to actually do a brute force search. We just go through all possible range, all possible numbers, and find out which one is actually the best. Which pair of numbers actually gives us the largest return, right? So now let's define another function. Let's do a get SMA max, right? The max is going to take a data frame as the input, and then max is going to be the largest number we're going to search, right? So for example, you don't want to actually use moving averages that has a window that's like 100 days long. If it's 100 days long, the moving averages are going to be very slow. It's going to be not really that responsive anymore. It's for short-term trading. If the window is too large, your reaction is going to be very slow, right? So we can set up a default value, say give like 60, right? That's going to be the maximum number we're going to search for, 60 days, right? Our moving averages is going to have a moving window that's equal to or shorter than 60 days, right? And then let's define some variables. SMR, say max equals to -1, right? And we're going to start with -1. It's supposed to be a floating point number, right? And then S max is going to equal to 0. L max is going to equal to 0, right? And then we're going to start with those initial values, and then during our iterations we're going to sort of change them, right? So for S in range 2 to n max. Okay, so I spelled it wrong, right? So it's 2 to n max, and then for L in range. So this is the short-term moving average window, right? Long-term moving average window is supposed to be longer than the short-term moving average window. So we're going to do what? We're going to start with S plus 1, right? And then end with n max plus 1, right? And then what's going to be our SMAR, that's what's going to be our moving average return for this particular S and L pair, right? For every S and L pair. All we have to do is to call get SMA return, right? Get SMA return df, that's our data frame, SL, that's the 2 iterators, right? And then do we want to make a plot for every iteration? No, we don't want to make a plot for every iteration. That's going to be too many plots, right? That's going to slow down our calculations by a huge margin, right? And then if SMAR is larger than SMAR max, then we're going to replace SMAR max with SMR, and then we're going to replace S max with S, and then L max with L, right? And that's pretty much our search, right? We're pretty much just doing this brute force search through all possible pairs in our range, which is given by mx, right? And all we have to do now is to actually return these search results, right? SMAR max, and then S max, and then L max, right? That's it, right?